Okay, this is part 2 of chapter 8's lecture. In part 1, we learned about point and interval estimation of the mean and proportion. What we will do now is learn about point and interval estimation for the difference in the mean and the difference in the proportions. So let me go to that. Dun, 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 dun. Where is it? Okay. Here. All right. This is section 5. Estimating the difference between two population means. Okay. So here, suppose we had two different populations, say men and women. And what we want to know is the difference in some characteristic, say income. Um, what is the average income for men who work, and what is the average income for women who work? We could consider men and women as two different populations. And inherently, in the United States, if we had data on every man in the United States and every woman in the United States, we could calculate their average income. Average income of men, say, is population 1, and population 2 would be the average income of women. And we could also calculate the variance and the standard deviation of the average income. Of course, most of the time, or almost all of the time, we don't have the money to collect data on every man in the United States and every woman in the United States. So what we do is we take samples. We draw a sample of N1 from population 1 and N2 from population 2, N1 being how large the sample. Say N1 is 1,000 men, N2 is 1,000 women. And given that we drew a sample of 1,000 men, we could calculate the sample mean and the sample variance. That's x1 bar and s1 squared. From the sample of women, 1,000 women, N2, we could calculate the average income for women, that's x2 bar, and the sample variance, s2 squared. Okay. So again, here's a summary table. The goal is to say something about the population parameters, mu1, mu2. And what we do is we take a sample to talk about and estimate population parameter differences. Remember, the goal here is the difference between two population means. So what we want to do is we want to see, is there a difference? If x1 bar minus x2 bar is equal to 0, maybe there isn't a difference. But if x1 bar is greater than x2 bar, that is saying the average for population 1 is larger than the average from population 2. All right. So properties of the sampling distribution of x1 bar minus x2 bar, of the difference in the two sample means. Okay. Let's look at this. When independent random samples of N1 and N2 are observed and are selected from the population with mean mu1 and mu2 and variance, these are populations, parameters, sigma 1 squared and sigma 2 squared respectively, the sampling distribution of the difference in the sample means have the following properties. The average, if you kept taking samples and calculate the difference in the sample averages, on average, that difference should equal to the population parameter differences of mu1 minus mu2. The standard deviation of the sample differences, sample average differences right here, should equal to the square root of the population parameter, population variance 1 squared divided by n1 plus population variance 2 squared divided by n2. Of course, we don't know these things. Sigma 1, sigma 2, we don't know those things, okay? So what we have to do is say, well, it's almost equal to the sample standard deviation, okay? Sample standard deviation of population 1, sample variance, sample variance of population 1, sample variance of population 2, okay? When we have a large sample size, N1 and N2 are large, then we could assume that the sampling distribution of the sample average differences is normally distributed. This is the central limit theorem again, okay? And how large is large sample? Well, we need both N1 and N2 to be 30 or more. We need the samples to be at least 30 or greater, okay? Don't worry about this Z statistic right now. This is not really important now. It's going to be important for chapter 9. But this is how to calculate the Z score, or the Z statistic. But don't worry about that now. It's not relevant for what we are going to do in this chapter. Okay, so last, large sample point estimation of mu1 minus mu2. So when you estimate the difference in the population averages, well, the point estimator is just the sample averages, okay? So if we want to just calculate a point estimate of the average in the population, we just take the sample averages. And for the interval, remember, we use point plus or minus z of half an alpha times the standard error. So this is the point estimate right here, the sample average differences, plus or minus z of half an alpha times the standard error. This is the standard error formula that I showed right here. And that's it. Okay, we'll go over an average after, we'll go over an example after I introduce to you population proportion differences. Okay, pretty much same thing, different formulas. So let's go over this real quickly. Estimating the difference between two binomial proportions. Okay. So again, we have two populations. Let's say we have people in Korea and people in the United States. And we want to know the proportion of men in Korea versus proportion of men in the United States. Something like that. There's other examples here. Death rate of surgery procedure 1 versus death rate of surgery procedure 2. Wage increase rate in firm 1 versus firm 2. Proportion of Democrat voters in Orange County versus LA County, stuff like that, okay? Well, the true population proportions of, say, men in the United States, the percentage of men or proportion of men versus the total population in US, and the true population proportion of men in Korea versus the total population, that's P1 and P2 respectively. And if we want to compare if we want to take the difference of those two, why would you take the difference? Again, like the sample, again, like the mean differences, if this difference is equal to 0, that means there is no difference in the percentage of men in US versus Korea. If it's greater than 0, then population 1, say that's United States, has more men versus in Korea compared to the total population. Okay, well, P1 minus P2 is the difference. And that's the difference between two binomial proportions. Okay, an estimate of P1 is just P1 hat the estimate of P2 is P2 hat. So the unbiased estimator of P1 minus P2 is just the sample difference, P1 hat minus P2 hat. Okay? To calculate P1 and P2 hats, it's just X1 divided by N1, X1 being, in my example, men in US, it'd be the number of men in US in our sample, number of men in our sample divided by the total of our sample, number of men in our sample in Korea divided by total of our sample in Korea, okay? X1 being number of men in the US in our sample, US men in our sample, divided by total sample of US people is N1, and X2 is number of Korean men divided by N2 is number of Koreans in our sample. Huh? All right. The standard error of P1 hat minus P2 hat, the difference in the sample proportions is this gobbledygook, which is P1 times 1 minus P1 divided by N1. Remember, sometimes P1 minus N1, we use Q1, and 1 minus P2, we use Q2, okay? Sometimes we switch off between, we label Q as 1 minus P, okay? But we don't know these P1s and Q1s. If we did, we wouldn't do this analysis. So we use the sample estimates to calculate the standard error. And this thingamabob, okay, the distribution, the sampling distribution of the difference in the sample proportions is distributed normally if N1 and N2 are large due to central limit theorem. Same thing as everything else we talked about in this chapter. We need large samples. Okay, how do we know if we have large samples? Well, P1 times N1 has to be greater than or equal to 5. Sometimes in some books, it's greater than. I think in this book, it's technically greater than or equal to, but it doesn't matter. You know, greater than or equal to or greater than. Q1 and N1 is greater than or equal to 5. P2 and N2 is greater than or equal to 5. And Q2 and N2 is greater than or equal to 5. Okay. The point estimator of the population proportion differences is just the sample proportion differences. And the interval estimate is just the point plus or minus the margin of error. Point is this, margin of error is Z of half an alpha times the standard error. It's always, the margin of error is always Z of half an alpha times the standard error. And this is the standard error formula. Given now that I introduced to you the difference in sample means and the difference in population, proportions, let's do a couple of examples of what I'm just talking about. So let's scroll up, go back to section 5. Where's section 5? Which is right here. Let's go to a couple of examples and do them. Let's do this one, example 8.9. The wearing qualities of two types of automobile tires were compared by the road test, testing samples of N1 equal to N2 tires. So basically, they want to know how long these tires from two different companies last. Let's say Bridgestone racing tires versus Michelin racing tires, okay? And they took a sample, let's say tire 1 and tire 2. They took a sample of 100 tires from each company, okay? And they found the following. This is X bar, or the sample, put it in the wrong place. X bar, which is the sample mean from tire 1, is 26,400. And from sample 2 is 25,100. And the sample standard variance, sample variance, S to the squared, That's 1,440,000. And for tire 2 is 1,960,000. Okay, so just copy this table. All right, so they say estimate the difference in the population means of the wear out rate and use a 99% confidence interval to do this interval estimation. So they want you to find the point and interval estimate. Okay. To do that, so we want point and interval estimate. And the interval, we're going to use 99% confidence. Okay. So in order to do this, let's do the point first. The point estimate is just the difference in the sample means. Now, here we have tire 1 has 26,400 and tire 2 average is 25,100. Okay. If I label this tire A, let me do this. Okay, tire A and tire B, you're like, okay, so which one do I call 1? You know, for the point estimate is sample average of population 1 minus sample average of population 2. Well, which one is 1 and which one is 2? Let's go back. This I don't need to do this. The rule of thumb is use the bigger number in the sample average. When you calculate these sample averages, the bigger number, use that as population 1. Okay. So the point estimate would be tire 1 minus tire 2 and not the other way around. Why? The rule of thumb is basically because we want the average to be greater than 0. It's a little harder to explain and present when the average is negative. It doesn't matter. It's just that it's just a rule of thumb to make presentation easier. That's all it is. Okay. So the rule of thumb is always put the bigger number as population 1, the bigger sample average as and then say that's population 1, and the smaller sample average, call that population 2. All right. Now let's do the interval estimate. And to that, we have to calculate the margin of error. And the margin of error consists of z of half an alpha and the standard error. So the standard error. So let's calculate z of half an alpha first. Well, first, let's figure out what the confidence interval was. That was 99%. Alpha is equal to 1 minus 99%. Okay. So then alpha divided by 2, this is equal to alpha divided by 2. So, okay. So then the z of half an alpha, remember how Excel calculates function works. If we want to calculate the z that cuts off half an alpha to the right, Excel calculates from left all the way to the cutoff point. So we need to calculate 1 minus alpha divided by 2. Okay. So then the z of half an alpha is equal to norm.s.inv of this guy. And that will give us the cutoff, which is 2.576. That puts 0.5% to the right tail and 99.5% to the left. Okay. The next thing we got to calculate is the standard error. And the standard error formula is right here, is S1 squared divided by N1 plus S2 squared divided by N2. Well, we got S1 squared and S2 squared. We got to divide it by n1 and n2 and square root it. See if we could do it in one. If you can't do it in one line, we could do it in two separate lines. I'm going to do part 1 and part 2. Part 1 will be s1 squared divided by n1. And part 2 is going to be s2 squared divided by n2. And then part 3, let's say we got to do it in baby steps, will be part 1 plus part 2. And then the standard error is we calculate the inside, we just have to square root part 3. This is equal to part 3 to the 0.5 or square root. And this is our standard error. So we have our standard error and our z. So the margin of error is equal to z of half an alpha times standard error is that. So then our estimate is upper, point, lower. The point is right here. And the upper is the point minus margin of error. Oh, no, it's plus. Duh. Point plus the margin of error. And the lower is point minus the margin of error. All right. So what does this mean? Okay. What does this mean? So we have the same answer. This means the difference in the wear rate for tire 1 minus tire 2 is between, I don't know, 800 miles to 1,775 miles with an average of 1,300 miles. That means with 99% certainty, we could say tire 1 generally lasts longer than tire 2. Okay, tire 1 will last longer than tire 2. And if someone asked by how much, you would say, well, between about 800 to 1,780 miles or something like that. Okay. With 99% certainty, we know tire 1 lasts longer than tire 2. That's what this one says. Okay. Now, let's say the lower was below 1. So it's like negative 1,000. What that means is that with 99% certainty, tire 1 will last less than tire 2 to tire 1 will last more than tire 2. Remember, the difference is negative to positive. So with 99% certainty, if someone asks, well, can you really tell me if tire 1 will last longer or tire 2 will last longer? I would say, no, I can't. Because tire 1 maybe lasts longer by 1,775 miles, or tire 2 lasts longer by 1,000 miles. I don't know. Maybe they're equal. So if we had a situation like this, we couldn't be certain that one of these tires lasts longer than the other. But we didn't have that. We had this situation. We could be certain with 99% certainty. 1%, we could be wrong. Okay. Let's do another one. I'll leave this, this other example for the mean for you. So we'll do one for the binomials, okay? We'll do, say, this one, example 8.11. A bond proposal for a school construction is on the ballot at the next city election. Okay, they're going to borrow money to build a school. The money from this bond issue will be used to build schools in a rapidly developing section of town, so like a newer section of town. And the remainder of the town Remainder will be used to renovate and update school buildings in the rest of the city. So basically, it's going to build a fancy new school in the new upcoming area of town, and the rest of the town just gets a little refurbishment. Now, what they want to do is assess how popular is this bond proposal? And is it going to be more popular for those in the newer area? Yeah, because they're getting a new school versus older area where they're just getting refurbished ghetto schools. To assess the popularity of the bond proposal, a random sample of 50 residents from the new area and 100 residents from the older areas are sampled. So, and we'll say new area and old area. And new area, they got 50, and old area, they got 100. Okay. And they found the following, where X, we're going to do X for favorable, favored bond, the bond. Okay. We're going to use that for X. And we have 38 out of 50 and 65 out of 100. So that means P hat, the estimated proportion, is equal to X divided by N for each. Okay. It's 0.76 and 0.65. Yep, that's what we got here. And then they say estimate the difference in the true proportions favoring the bond proposal with 99% confidence. So they basically say get the point estimate and confidence interval of 99%, interval estimate of 99%. So to do this, let's first calculate the point. And that is equal to, and again here, just like the sample averages, we want the number to be usually positive when we present it, the rule of thumb. So here we have new is 0.76 and old is 0.65. We want new to be population 1 and old to be population 2. Again, that's because presentation purposes, we want this number, the difference, to be positive and not negative. It's only for presentation purposes, nothing more than that. Okay, margin of error. That is equal to Z of alpha divided by 2 times the standard error. So let's calculate the Z of alpha divided by 2 first. Okay. In order for us to calculate the Z of alpha divided by 2, let's get what the confidence interval is. That is equal to 99%. That means alpha is equal to 1 minus confidence interval. That means let's do this as percentages. And then alpha divided by 2, that's just alpha divided by 2. And for us to get the Z of alpha divided by 2, using Excel, we're going to have to calculate 1 minus alpha divided by 2, which is equal to 1 minus this dude. So then alpha Z of alpha divided by 2, or the cutoff number that puts 0.5% to the right and 99.5% to the left, is equal to norm.s.inv. That gets us the number. Put in this cumulative probability of 99.5 from left to right. And this is what the number is. Okay. Again, we calculated this in the previous example. Doesn't change. All the problems, it's the same thing. All right, for the standard error, that's a little complicated formula. It's P1 hat times Q1 hat, or 1 minus P1 hat divided by N1 plus P2 hat times 1 minus P2 hat, or Q2 hat. divide by into all of it square rooted. Looks complicated. So to calculate the standard error, we're going to do it in parts. We're going to do part 1. Let's do part 2. Let's just make part 3. So my goal is to do this as part 1, this as part 2, the sum as part 3, and square root. Okay. So part 1 is P. Oh, I didn't do calculate a Q, huh? Well, that's okay. We'll do 1 minus P divided by N. Okay. And part 2 is P times 1 minus P divided by N. And part 3 is you add them together. And then the standard error is part 3 to the 0.5. And there it is. And then the margin of error is standard error times z of alpha divided by 2. So this is the margin of error. So then our estimate is upper point lower, and the point we've already estimated as 11%. Okay, remember these are the proportions or percent, and it's probably looks nicer if it's percentages. And the upper is point plus the margin of error. Lower is point minus the margin of error. Okay. Make sure these are correct. Let's look at the answer. Yep, 30.82, 11, and negative 8.82. Now, this is exactly what I wanted, what I talked about with regards to, with 99% certainty if the difference is positive. Here, we can't say that. With 99% certainty or confidence, 99% confidence, we believe the difference between population 1 or people in the new area that support the bond versus people in the old area support the bond is about 11%. And our 99% confidence bound is between -9 to 30%. What does that mean? That means at the high end, it looks like newer area support the bond by 30.82 percentage points more than the old area. It's a huge support from the new area relative to the old area. But at the low end, it looks like the old area supports the bond by almost 9%, 8.82 percentage points more than the new area. So with 99% confidence, can we say the new area supports the bond more than the old area? No, we cannot say that. We cannot say that. It looks like there's no difference. It is possible that there's no difference in support from the new area and the old area. All right, the next thing I want to talk about is one-sided confidence bounds. What is a one-sided confidence bound? Well, here we were doing upper and lower. So we're doing upper and lower bounds or two-sided confidence bounds. A one-sided is a situation where you only care about the upper end or the lower end. That's it. You don't care about the other side. Okay. Sometimes an experimenter is only interested in only one of the limits, the upper limit or the lower limit. Okay. So then to calculate this, if we only care about the lower limit, it's point minus margin of error, look, it's z of alpha, not z of alpha, because the all of the error goes to one side. We don't have to split it to two different tails. And that's multiplied by the standard error. If it's the upper, then it's point plus z of alpha, again, one-sided, times the standard error of the estimate. Okay. Again, no need to find alpha divided by 2 because we're putting all of the error probability on one side. Okay. Here it is. We put them all on one side. So let's look at, let's do this one. Example 8.12. A corporation plans to issue some short-term notes, a loan requiring the borrower to pay. So short-term notes is a short-term bond. Okay, and they're saying, well, these are within 1 year. And is hoping that the interest rate that it has to pay will not exceed 11.5%. So they only care about the upper bound. Okay, they don't want it to exceed 11.5%. They don't care if it's 1%. They just don't want it to be 12%. To obtain some information about this problem, the corporation marketed 40 notes, one through each of 40 brokers. So I'm thinking sample is 40. The mean and standard deviation of the 40 interest rates were the following. So the sample mean is 10.3%. And they say standard deviation is equal to 0.31%. Okay. The corporation is interested in only an upper limit, right? They don't want it to exceed 11.5. Find a 95% confidence bound on the upper part, right? So let's do this. Find point and 95% confidence on upper bound. So that's what they want you to do. All right. So this is a single, there's no like difference in the means and whatnot. This is only a single average. There's no it's a single average of interest rates. It's not a proportion or anything like that. So let's look at the formula we need to use. Scroll up. And the mean, we have the mean. And the standard error is the standard deviation, which we have here, divided by square root of n. Okay, let's scroll down. Oh, which is right here. All right, so let's calculate the standard error. This is equal to standard deviation divided by square root of n. So n to the 0.5. Okay, and I put parentheses around this. So I know the square root only happens to the standard deviation. Okay, I'm just being paranoid there. Nope, I guess we'll do it that way. All right, I can make it a percentage. Let's just do percentage. Okay, let's do that. All right. So to do the 95, so we have the point, okay, so let's do the point. Point estimate is just the sample average. The point estimate of the population parameter is the sample statistic or the sample average here. And then we want to find the margin of error for an upper bound only. So we need to find z of alpha, not half an alpha, and the standard error, which I've already calculated. So confidence interval is 95%. Alpha is equal to 1 minus 95%. And so to calculate z of alpha, this is equal to, we want to calculate up to the 95%. We want to get a cutoff number that has 95% from left to right, and the right tail is 5%. So here it's easier. That's just 95% we use. So it's norm.s.imv of 95%, because 95% to the left and 5% is in the tail. And there it is. So the margin of error is standard error times z of alpha is right there. So then the estimate is upper only, and point is right here, and upper is the point plus the margin of error. Oh, Jesus. Let's make sure this is correct. That's right there. Yeah, 10.38, 10.38%, 10.30, 10.30. So with 95% confidence, we're pretty sure with 95% confidence that the interest rate that this corporation will get will not exceed 11.5. It's going to get up to 10.38 only. That's 95% confidence. Okay. You can estimate that the mean interest rate that the corporation will have, the population interest rate, the population mean, or the mean interest rate that the corporation will have to pay is probably less than 11.5 is pretty, you're pretty confident. It's going to be 95% confident that's going to be less than 10.38. Okay. Okay. The last thing we're going to talk about, section 8, is choosing a sample. And this is basically manipulating the confidence interval formula to figure out, if I want a certain confidence interval, how big does our sample needs to be? Okay, for example, do you remember? Here's a confidence interval formula is the mean plus or minus the margin of error, and the margin of error is a function of standard error, and the standard error is a function of sample size. So we're going to solve this formula for n, and we're going to put other things in there and find what n has to be. Okay, I know that sounds weird, so let's go through it. Designing an experiment is essentially a plan for buying a certain amount of information. Okay, so the price of statistical information varies depending on how and where the information is collected, and you should buy as much statistical information as you can for the minimum possible cost. The total amount of information in a sample is controlled by two factors: the sampling plan or the experimental design, and the sample size n. Okay, we're going to talk about n here. All right. So how to choose the sample size? Determine the parameter to be estimated and the standard error of its point estimator. Then proceed as follows. So first determine the parameter to be estimated, whether it's a sample mean, whether it's the population mean, population proportion, or the difference in the means from two populations, or the difference in the proportions of two populations, okay? And the standard error that you want. Choose B, the bound on the error of your estimate, and the confidence coefficient, whether you want 99%, 95% confidence. Okay. For one sample problem, solve this equation for the sample size n. Okay. So what you want is you want z of alpha divided by 2, or half an alpha, times the standard error to be less than or equal to b, the bound. Okay. For two sample problem, when you have the difference in two populations, okay, set n1 and n2 equal to n. So you want to make sure both samples are equal and solve this equation. Okay. I know it sounds weird and complicated, but it's really easy. And let's solve example 8.13. Example 8.13. Okay. A manufacturer wants to estimate the average daily yield mu of a chemical process, and he wants the margin of error to be less than 4 tons. He wants the margin of error to be less than, equal to, or less than 4 tons. 4. It is known from prior studies that standard deviation is about 21. How many measurements should be included in his samples, assuming confidence interval of 95%? Okay. So here we're talking about the average daily yield mu. So this is only a one population issue. And we're going to use the formula okay, of the following. So let's solve it out together. So we have margin of error is equal to z of alpha divided by 2 times the standard error. And this is equal to z of alpha divided by 2 times standard error. Here is sigma divided by square root of n. Okay. And this is equal to the margin of error. Now we need to solve for n, because they're trying to say, well, how many measurements does he need? Or how big does a sample have to be? Okay. So what we're going to have to do is the following. We're going to solve for this formula. We just want the margin of error to be less than 4. Okay. So we want this gobbledygook to be less than 4. Remember, the margin error is this gobbledygook. We want that to be less than 4. Okay. So we have z of alpha divided by 2 times sigma divided by square root of n is less than 4. I'm going to put this guy up here and this guy down here. So z of alpha divided by 2 times sigma divided by 4 is less than square root of n. Okay. And then we're going to square both sides. So z of alpha divided by 2 times sigma divided by 4 squared is less than n. So we just have to find z of alpha divided by 2 and sigma, which we have here. Okay. Square it. And then we know that this number, whatever it is, okay, we need to have an n that's greater than this number. Okay, so here's the formula. Let me put this formula somewhere. Right here. And this, let's delete. All right, so let's do this. Okay, so let's calculate it. So we know what sigma is. That's 4. Sorry. We know what sigma is, which is 21. Duh, sorry. That's 21. So sigma is 21. So I need to calculate z of alpha divided by 2. So we know what confidence interval is. That's 95. So then alpha is alpha is equal to 1 minus 95. So 5%. Alpha divided by 2 is equal to this guy divided by 2, 2.5%. So 1 minus alpha divided by 2. This is 1 minus this dude. So what we need to do is find a z of alpha divided by 2. And in order to do this, we need a cutoff. That's the cutoff that puts 97%, 97.5% to the left of it. So norm.s.inv of 97.5, that puts 2.5% to the right, or half an alpha to the right, is 1.96. Okay. All right, so we got 1.96 is this dude plus 21 divided by 4. So let's calculate this. We have let's calculate this thingamabob. I'll call this thingy. And this is equal to 1.96 times 21 divided by 4. And this thingy has to be squared. $105.88. So what does this mean? It means this thingy right here, okay, oops, this whole thingy is equal to 105.88. N has to be greater than 105.88. So we need to choose a sample of at least 106. Okay. To ensure a margin of error less than 4. Using a sample size of n of 106 or larger, you could be reasonably certain with the probability equal to 95% that your estimate of the average yield will be within plus or minus 4 tons. We want the margin of error to be 4. Okay. So it's basically solving that margin of error problem for n. That's all it is. All right. Clear that. And there's another one here for you guys to do. I advise you guys to practice again. And we're done. At the end, I have a bunch of parameters, mu, the difference in the population mean, differences in 2 population mean, proportion, difference in 2 population proportion, the point estimator, okay, sample sizes, and the assumptions that you need, okay. All right, we are done, okay, with this lecture and lecture on chapter 8. Okay. Have a good day.